Hey, Michael, how are you?
How you doing? Was that a powder rheometer? I think I see the FT4 there in the top left.
Yeah, I'm running the powder rheometer, some advanced powder characterization. So what I'm doing right now is I just emptied this material out. Give me 1 second here. So I'm prepping the material here. I got my powder sample here, and I started using this 48 millimeter propeller here. Basically what this did was it prepped the material, got rid of any clumps, agglomeration, and aerated material, kind of prepping the material. Now, I just got done using this vented piston. Basically what this does is it applies a normal stress to the powder bed to 15 kilopascals. Not tablet compression, megapascal. We're dealing in kilopascals just to consolidate that material. So that's what this vented piston does. Now the last step here, Michael, is I'm going to put on the shear-cell piston here, because now we're going to start actually measuring the shear-cell data here. So let me
Oh, you're putting that up in there. I guess my next question would be why would we want to do this? What's the intent of using powder rheometer? What are we trying to see?
Well, this is for advanced characterization, Michael. So last episode, we talked about micromeritics, or Hausner ratio, bulk tap density. We talked about compressibility index. We talked about particle size distribution, angle repose. This is a more advanced way of measuring the powder flow.
Okay.
So let me hit the start button here.
Does this also tell us things about like cohesion as well?
Yes, we're going to talk about cohesion, adhesion. Here comes the piston here. This is a shear cell. And basically what we're doing, we're looking at normal stress applied and shear stress in kilopascals. And it's going to run it at different pressures. It's going to run it at 5, 6, 7, 8, 9, and 15 kilopascals. So it's going to keep adding a little bit more and more pressure. And again, it's measuring normal stress we're applying and the shear stress. So this is going to take about 20 minutes of running. But yeah, this is the process. Again, we got these three rods here. We got the 48 millimeter propeller for aerating and getting rid of agglomeration. We got the vented piston. This will apply that normal stress to get the powder consolidated. And then we got the shear cell piston on there to apply, again, normal stress and shear stress, which you can see we're actually measuring right now normal. And here comes the shear stress.
So yeah, everybody, if you haven't figured it out by now, episode 6, we're going to go over powder rheometer technology and what to do with it, why it's important, how to understand the data, and we actually have a special guest we're going to bring on here in a second. So I guess, Robert, we're going to let this thing run, kind of do its business, and then we'll go introduce our special guest.
All right.
So let's let Robert get over to his tabletop here. All right.
Welcome back.
Yeah, episode 6. This has been fun. So today's special guest, he's been a scientist, I think, for about 12 to 15 years. We're gonna have him introduce himself. His name is Dr. Rahul Hawari. So here, come on, Rahul.
Good morning.
Hey, how are you, Dr. Hawari?
Doing fine. How about you guys doing?
Great. Excellent.
Yeah, Rahul, would you like to introduce yourself? So kind of give us a little bit of background.
Sure. So, welcome everyone. I'm Dr. Rahul Hawari. I'm serving here as a Director of Scientific Support at Natoli Scientific. I have more than 12 years of experience in powder compression physics and pharmaceutical material science. So here at Natoli Scientific, we are developing the formulations as well as troubleshooting the scale-up failures by integration of advanced material science. So here today we are gonna talk about how can we assess the powder flow of challenging powders when traditional methodologies like Hausner ratio and compressibility index doesn't help us to distinguish the powder properties. So that's what Robert was doing. He was using advanced characterization tool FT4 Rheometer, and I'm gonna go through the details of that methodology.
Okay. So, do you have something to present to us today?
Yeah.
Okay.
So let's talk about interesting facts about tableting. So when you have your powder here in hopper, you are expecting non-cohesive behavior in order to flow better. Moment that powder goes in the die cavity, what are you expecting? You are expecting powder should be very cohesive to make a stronger tablet. So in milliseconds, you are expecting 180-degree change in the powder behavior. So when powder should be here in hopper, it should be non-cohesive. When it is here in die cavity, it should be cohesive. So definitely we are asking a lot to that powder. And that's why we need that balanced behavior in fractions of millisecond. And that's why when people are saying tableting is very easy, I'm not 100% agree with that one.
Yeah, I agree with you, Rahul.
Yeah, I think we'd all agree.
So this is the current powder flow characterization methodologies where we have this Hausner ratio compressibility index, which is technically based on basic powder micromeritics like bulk density and tap density. So it is a ratio of tap to bulk density. And as you can see here, the scale goes from 1 to 1.60. When it is a 1, it means that powder has perfect or excellent flow where bulk density is equal to tap density technically.
Right.
Now,
Not reducing in volume when you're going through the tap density apparatus we showed in the last episode.
absolutely. So are these methodologies are very distinctive? Not really. That's why we have this FT4 Rheometer. So what Robert has done just now, he was talking about this chopper blade. I will call it as a chopper blade. It was chopping the powder, chopping the air pockets, and bringing all powder particles on the same page. Once we have that, then second thing was the consolidation, where we are applying normal stress or compression stress, just like tableting, but in kilopascal, not in megapascal.
Right.
And
So
then
for
we
these
are,
two steps, you're basically trying to like normalize the powder in the cylinder
Yes.
across the spectrum is what you're doing.
yes, first we are normalizing powder, and then we are consolidating powder. And now
Yeah.
what he did, and you have seen that he was scraping up extra powder.
Yeah. Now, remember last time, Michael, we used dicalcium phosphate, M-compress, and microcrystalline cellulose, very low bulk density. So if we were going to run the powder rheometer, they're going to have different densities and fills. So keep everything consistent. So that's what Rahul's talking about, prepping everything for consistency.
Absolutely. And now once we have this cohesive powder, or once we have powder cohesion, what we want to do, we want to apply shear stress. We want to disturb that powder. So technically we want to know, once powder has cohesion, how much shear stress I need to disturb that powder. And that will be the measure of the powder flow properties. So as I said just now, with all this preparation, what we want to do, how much shear stress we need to disturb that powder cohesion.
And just so we understand here, the shear stress you're talking about, when that head spins, it's measuring when the powder actually breaks. I guess the cohesion between particles and allows that, what amount of force it took to get the powder to move from that rotation. That's what we're measuring, correct?
Absolutely, because shear stress is in this direction and normal stress is in this direction, like in perpendicular direction and in parallel direction. So now, and that has been done by one gentleman long way back, Morse circle. What he did, he plotted shear stress versus normal stress. Then this is the equation, tau is equal to C plus sigma tan theta. I will go in the details of that one in next couple of slides. So let's talk about Morse circle. So first is a normal stress, which is on x-axis, and Robert was saying he applied 15 kilopascal
Right.
normal stress.
This is the downward pressure.
Yes,
everybody who's watching, this is the downward pressure that we're applying to the material in that cylinder.
Just like a tableting, the way you are applying compression pressure in tableting.
Yeah.
Now, on y-axis we have shear stress, which is in parallel direction, because the solid plates, we want to disturb solid plates in parallel direction, just like liquid plates. And that shear stress is in, again, kilopascal. Now Robert applied 15 kilopascal. I'm a little bit frugal here. I have applied, let's say, 10 kilopascal normal stress. And let's assume that I require 10 kilopascal shear stress to disturb that cohesion, powder cohesion. And therefore, when I'm going in this plane, I have capability to disturb that powder cohesion. And that's why I am calling it as a failure plane. Now, what I want to do, I want to make an angle which is passing through the origin, and that is called as failure envelope. And now from this intercept, I want to draw a 90-degree angle here. So by the way, this is the shearing angle, and then this is 90-degree angle here. And that whole length is a radius for my Mohr circle. And that is the center of Mohr circle, and then I can draw a Mohr circle. Okay. So that first thing is minor principal stress, and second one, that is sigma 1. This one is a major principal stress, that is a sigma 2. And we will keep visiting that one.
So back on that chart there, Rahul, just so I understand here, that failure plane is that disturbance, that rotational disturbance, right? And then that helps us define where that shear angle is. Now we picked 10 kilopascals. Why didn't we pick 15 or 20? What's the defining factor of what pressure should we run, or should we be running multiple pressures here?
Yes, absolutely. So we'll be running, let's say, I just took an example of 10 kilopascal. The way we look at it as like we are initially applying lower normal stress, like 5 kilopascal, then 10, 15, 20, something like that. So we want to create several more circles. And we want to see when we are applying when we are applying the normal stress, how is the respective shear stress? Is it going in proportional direction or in other direction? So that's the reason we just don't want to apply one shear stress, one normal stress, and we want to find one shear stress. So we keep making like 3 to 5 more circles.
So you're saying it's important to run multiple pressures and increment, so that way you can normalize what the actual powder behavior is by fitting the rest of the data together.
Absolutely. And please keep in mind, everything is in kilopascal, not in megapascal.
Yes, very, very small amount of pressure.
Yes. And if that kind of small amount of pressure, if powder is still creating a problem, then definitely we need to think of. So as you can see here, there are like 1, 2, 3, 4, and 5. And that's what Michael was making the point here. We are applying small normal stresses, and we are finding out respective shear stress. Then we are keep increasing the normal stresses, and we are finding out how much shear stress we need to disturb that powder. And then we get this, we draw the tangential line here. And this y-intercept is c. So because this is a straight line equation, y is equal to mx plus c. So c is a y-intercept, which is a cohesion. So higher the cohesion, you will have very problematic powder. And that's you cannot capture with your Hausner ratio and compressibility index. Now, then you are drawing the tangential line, as I said, and then this angle is called as angle of internal friction. So how much internal friction powder has? If powder has irregular shaped particles or irregular shaped morphology, then you have lots of internal friction, and that can help more cohesion. And that powder will be, again, challenging powder. Okay. So this is the data which we have run on various model materials like MCC 102, starch 1500, sperolac, incompress, and these are the Hausner ratios. As you can see here, Hausner ratio is decreasing from top to bottom, specifically from MCC 102 to incompress. And look at the cohesion. MCC 102, we know that it is highly cohesive powder, so it has highest cohesion. And with incompress, surprisingly, we got negative cohesion coefficient. So what does that mean? What are lowest normal stress we are applying? It is not really consolidating that powder. So in compress, it is not highly cohesive, so it requires more cohesion. So just like instead of applying 5 kilopascal, we might want to increase with like 10 or 20, and then we might not get this negative intercept. And then we will be able to find out this flow function, which is a ratio of major principal stress and then unconfined yield strength. And technically it should be a stress, not strength, because we are dealing with x-axis. Unfortunately, people coined this term, wrong term, back in 1960, because I was looking in the history. So Jenike, he did that work in bulk solids, and he coined this term. It should be unconfined yield stress, not strength, because they do have different meaning in physics. So now, as you can see here, we have Hausner ratio, which is not distinctive. And look at, we have several parameters which are based on powder morphology, powder flow, powder cohesion, and powder dimensions, also particle dimensions and particle morphology. And what we did here at Natoli, I come up with the normalized flow score based on Mohr circle parameters. And these are some equations. If you are more interested in these equations, please visit us in 2026 AAPS in New Orleans, where we will be going
Yes.
more about these ones. And we will have quite good amount of database. And then we come up with this normalized flow score. So excellent, good, moderate, poor, and very poor. But this score is based on important powder properties like cohesion, major principal stress, unconfined yield stress, as well as flow function and angle of internal friction. And look at the classification.
Yeah, I would like to mention, just like with the Hausner ratio compressibility index, you've got, poor, very poor, very, very poor, right? I think you have those. So you see MCC 102 is at poor. Doesn't mean you can't run it, just mean you can have some challenges. But when you get to very poor, then those are usually where you need to reformulate, granulate, or something needs to change. You agree with that, Rahul?
Absolutely.
Yeah.
You are on spot on. Yeah, so you have like excellent, good, moderate, and poor. So as we know that these metals, they are flowing nicely. Now we have some challenges with incompress. As I said, what are the normal stress we applied? It is not sufficient, and that's why we don't have flow function. So this methodology definitely needs some refinement, but it will be a really good methodology and good alternative for Hausner ratio and compressibility index, specifically for the challenging powders.
Okay. All right. Well, I think we're 3 minutes over, so we can start taking some questions. But going back to this this comment here, I guess by Robert, the categorization, that classification right there is kind of a guiding line of what we should be looking at. But it also, I guess, by testing individual powders or excipients, kind of gives us a goalpost of what we should be incorporating to balance out our powder mechanics, right? So we'll get some excellence, some goods. And then will this also be an inverse indicator of, I guess, compressibility? If it's a very good flowing powder, not very cohesive, would this also indicate that in a negative perspective, that it also is not compressive when looking at this scale?
Absolutely, but please keep in mind, we want to have a balance between non-cohesiveness and cohesiveness, because we don't want just non-cohesive powder. It will flow nicely, but at the same time, your end goal is to make a good tablet, not to make a powder, isn't it? So,
yeah. So there's a balance, right? So you need some cohesiveness when you're compacting and creating bonding of the particle-particle interaction, which kind of segues us to another kind of topic here about sticking. Where does sticking come from, right? So when you're compressing and compacting your powders, you want your particles to bond to each other. If they don't bond to each other, they're sticking to your punch face. Now that's the relationship between cohesion and adhesion, right, Rahul?
absolutely. And then at Natoli Scientific, we come up with new technology for sticking index, because when you are in late phase of your development, then you cannot change your formulation. So to whom you want to blame? Well, you want to blame it everything on tools.
The
And
punches, right?
punches. So
Yeah,
there,
we're gonna have an actual episode dedicated to this because this is such a hot topic
Oh,
all
yes.
the time. Our next episode is going to be completely on the sticking index, how we quantify it, how we measure it, and then how to utilize it in your process.
Using powderiometer.
absolutely. And that is an in-house technology in collaboration with Long Island University, of course.
Yes. Yeah, so this will be great. So not only are we using the rheometer for powder flow cohesion, but we're also going to use it to assess sticking. It's a material sparing approach, so you don't need kilos and kilos of product and new tooling to test it on your tablet press. All you need is how much material you need for this, Rahul?
Depending on bulk density, we require between 50 grams to 75 grams.
So only 50 to 75 grams. You don't have to purchase the tools yet. We've got these steel coupons made of different steels like M340, chromium nitride, zirconium, just all the different steel types and coatings that are offered by Natoli. We make them out of these, basically the steel discs that go in the bottom of your powder rheometer, and then we could run the machine and we get the sticking index. So yeah, we look forward to that. So when are we holding that one? Is that going to be late August?
I think that's late August. I don't think we finalized the date, but we're looking, I think the last week of August, maybe the 25th.
August 25th. Yeah, look for us on social media for confirming that.
Yeah. So anybody that's on LinkedIn versus YouTube, remember on YouTube, you use the super chats to ask questions. If you're on LinkedIn, all you need to do is post a comment in the event as you're watching it, and then it'll show up here in stream, and we can start answering your questions from there.
Right. How much time do we have, Michael?
We only have about 3 minutes left.
Okay, great.
So I guess we're waiting on questions coming in. Go ahead, Robert.
I was going to say, yeah, we have a few more minutes for questions if anyone wants to jump in. If not, you can reach out to us. You'll see on the bottom of the screen here, if you need any help with your powder flow, compression, sticking, CT scanning, X-ray, that's another episode we're talking about, scale up, reach out to us here and we'll be happy to hold a one-on-one meeting with you and kind of, troubleshoot your problem and address your issue and fix it.
Yeah, we cover many aspects of tableting issues. From sticking, picking, capping, lamination, core erosion, chipping, abrasion. So we cover the gamut. So please reach out to us if you're having any types of tableting issues. But I guess I did have another question. We want to go back to your data chart, Rahul, while we're waiting on questions here. I had one other question.
Which one? This one or previous one?
Go back to your chart of data where we're going through the Moore circle. Back one more. I think maybe one more. Okay. Back. Okay. Yeah. No. This here. So the tangent line you're drawing is the best fit line for all of those, and the angle of internal friction. How is that playing into the flow function characterization? What is that? How is that calculated and put into that flow function?
So the way I have done is I have used those equations specifically to integrate all these factors. Okay. If I understand correctly, first is like how it is impacting the powder flow, isn't it? Okay. So when powder has like irregular shaped particles, then what will happen? They will have higher friction. Like spherical particles, they have less contact area with each other. That's why they will have less friction. That's why spherical particles, they flow nicely. But when you have irregular shaped particles, there will be mechanical interlocking and more friction. And that's why they will have more cohesion. So in general, higher the angle of internal friction, you will have possibly high cohesion. Just like here, as you can see, MCC 102, it has a fibrous particles, and that's the reason it has like 37.65 degrees angle of internal friction. And that's why it has high cohesion.
So then based upon that description, you have to combine the angle of internal friction as well as the flow function to actually understand how the powder is going to perform cohesively as well as flowing.
Absolutely. And that's the special about this normalized flow score, because it integrates all these parameters. So it is a inclusive thing rather than exclusive thing.
Okay. Well,
Wonderful.
everybody, I think, go ahead.
And that's the real beauty of this new score, because and that will help you to identify challenging powders, because sometimes this Hausner ratio is very misleading. One of the reasons is the accuracy of measurement of bulk and tap density, because though it is given in 2 significant digits, unfortunately you can't measure the bulk and tap density with that kind of accuracy.
Right.
Okay. Well, that's our time here. So thank you, everyone, for joining episode 6. We're going to schedule episode 7, which will cover the sticky index in August, probably August 25th. Robert, Rahul, you want to say anything for closing out?
Well, I'd like to say thank you, Dr. Haware, for special guest today. We'll see you again in about a month, but we appreciate your knowledge, insights, and your research. So thank you.
Thank you for giving me an opportunity, and looking forward to some interesting questions and next episode also.
Yes,
Stay tuned.
Thank you, Doctor.
Thank you.
All right.